Hello. So let's look into today's Leetcode problem, which is shortest distance after road addition queries 1. Though the question might sound very lengthy, but it's pretty straightforward. In this question, you are given with a total of n cities, and these cities are named from 0 to n minus 1, and these cities also have some initial configurations, so they are connected with each other directly and not indirectly. By directly, what I mean is ith city will have connection to I plus 1th city. You should simply ignore this connection 2 to 4 because it is some connection that is made later on at the point. So these connections are unidirectional, they are not bidirectional, and the cost of these connections are also having unit cost only. So they are unweighted, at the same time they are directional, that too unidirectional. So at some point of time, few additional connections are also made, but your primary goal is to return the minimum cost in order for someone to start from node 0 to node n minus 1. So after each connection, you will be calculating the minimum cost to reach node n minus 1 from the starting node. So that's the question. And yeah, so for some question like this, you should always think about two algorithms whenever you are asked to calculate the shortest distance. Given you are given with the starting point, and if you want to calculate the shortest cost or minimum cost in order to reach any other cities, then the two algorithm that should come into your mind is Dijkstra algorithm or Bellman-4 algorithm, because these two algorithms primarily focus on calculating the minimum distance from a fixed starting point to all other nodes. So in this question, I've used Dijkstra algorithm for the reason being it providing better time complexity. It is a little different variation of Dijkstra algorithm, but with that variation, we were able to optimize the time complexity. So let's quickly look into one of the examples here. And before, yeah, I can actually walk through the example in order to make things a little clearer. Then I can go through the code as well. So let's consider a city which is like this initially, and they are saying that they will be adding a connection from 2 to 5. So initially, the cost to reach fifth node from 0th node will be 1, 2, 3, 4, 5. 5 will be the minimum cost. But after insertion of first query, the cost will shift down to 1, 2, 3. Yeah. Let's say if you add one more connection, that is from node 1 to node 5, the cost will shift to 1 plus 1, that is equal to 2. So after doing the connections, you will have to return the vector of minimum cost in order to reach the end city. So the answer should look like 3 comma 2. So yeah, that's the explanation on what we are expected to return. And the Dijkstra algorithm part is kind of straightforward. Let's look into our implementation of Dijkstra algorithm. Okay. So initially what we do is, okay, so the input that we are provided with is basically n, that is the total number of cities, and then the connections. So we are not given with any adjacency list. So in this code, as you can see, I am forming an adjacency list with ith node having connection to I plus 1th node, and its cost is 1. So the first index is basically the destination node, and the second one is the cost. Now, what we are trying to do is, for each of the queries, we want to return the minimum cost to last city, the nth city, n minus 1th city. So for each query, we are pushing that connection in adjacency list. So the query is basically starting node to ending node. So on the index of starting node, we will be pushing ending node with unit cost. And after that, one thing that you should be noticing here is every time we do the iteration over queries, right? We will be defining a fresh cost matrix, and initially we will be setting a very high value on the cost matrix in order to do relaxation for Dijkstra algorithm. And cost for zeroth node to reach zero should always be zero. Okay, these two things should be encountered now. And the next thing that we are doing is call the Dijkstra algorithm. I've named it as helper over here. So this function takes two arguments, which is adjacency list and cost. So let's look into Dijkstra algorithm here. So I'm setting up a priority queue, and obviously we are going to compare the cost for setting the priority here. So I've defined a comparator here as well for getting the min heap properties. And let's start to begin with the priority queue. So initially we will be pushing 0 comma 0, that is the destination node and the cost to that destination node. So start node and destination node are same here, so we'll be pushing 0 comma 0 and do the pop, traverse the neighbor, and if we find a better neighbor, better cost to that city, we update it and push that neighbor as well for further exploration. That is how Dijkstra algorithm works. And in the end, what we do is return the cost for n minus 1th city that is being stored in the resultant array. But one thing to notice here is for every iteration, we are going to use the same new cost array every time, and we will have to do traversal on all of the nodes or like every time when you insert a new query, and because of that the time complexity of our solution will increase. So I actually did submit a little brute force kind of solution here, and you can see the runtime took a lot of time, and the memory also was a little higher on this solution. Then the other solution that I wanted to do is it was basically an optimization of the solution. So I was like, we already are doing traversal starting from the first query itself. Why to do it again? We can simply try to insert the newly added connection into the queue and start doing the exploration. If things make sense, if relaxation happens, that is when we are going to do exploration on remaining of the nodes. Apart from that, you might not need it, right? So that is when I arrived at this solution. Okay, so this is the solution. So here I am okay. So in this solution, what I am trying to do is you can see that I am not re-declaring the cost array every time we iterate through the queries here. I am simply passing the same cost array. The only addition to this algorithm is that initially what we usually do is we relax the edge and push the node, right? Here you can see we relax the edge and push the node. Similarly, we do a check here as well. So before adding the query in, before exploring the query or adding the query, we will be checking if adding this query, adding this connection relaxes the edge or not. If it relaxes the edge, then we do the relaxation part and then push that connection to the query and do exploration for that node as well. That is the only change that we are doing there. So instead of traversing, instead of making the priority queue iterate the same nodes again and again, we would want to iterate the newer connections that's being formed. And if the newer connections don't really do any kind of relaxation, we don't even need to traverse that node. So that is why I have put the condition over here as if we have a relaxation, if we find a better path, then we push it into the array and try to improve the solution, try to improve the cost array. So that's pretty much it. And in the end, what we do is we return the cost to n minus 1th node. and store it in the result, that is the array, and then return it. And if you try to submit it, right, you can see a significant difference in runtime as well as memory here. So yeah, that's pretty much it for this solution. Thanks for watching. Bye bye.